So experiment number 3, single phase full bridge inverters. You are making two circuits. Well, you're making one circuit, but you're changing two different types of loads to test the output of a full bridge inverter circuit, which is here, that we discussed in the class. So first circuit is when your load is a resistive load, and the second circuit when it is resistive, it is a resistor and inductor. So it's an inductive load. The switching frequency is 60 Hertz, so the output waveform will have a 60 Hertz frequency or 1 over 60 Hertz time period. Since you're making the lab report, you don't really have to create the output waveform. You know what the output waveform looks like. It is discussed in the lecture. So in this circuit, all the values actually are given to you. These are the MOSFET switches, and pulse width is 8.3 millisecond, which is half of the time period, which is 16.7 millisecond. That corresponds to 60 Hertz frequency. So first, as you can see, time delay is 0 for M1 and M4. So first, these two MOSFETs are going to turn on, and then when the pulse width, which is 8.3 millisecond, when it is going to turn off after 8.3 millisecond, then these two MOSFETs are going to turn on, because the time delay is 8.3 millisecond for these two. What you're expecting here is a good square wave at the output with the values of 20 volt and negative 20 volt. So let me go ahead and show you. Oops, not this. Okay, so this is the output of the first circuit. When you're putting waveforms in report, make sure to make the line with a little more than what it is by default, because it is easier to see if it is a little bolder. So this is the output of the first circuit. As you can see, 20 volt, negative 20 volt. Q1 is on over, sorry, not Q1. M1 and M4 are on over here, and M2 and M3 are on over here. Go back. Okay, in the next one, you have to derive the Fourier series of the output waveform, voltage waveform. This was done in the class, and the expression is present in the lecture notes. And from the Fourier series, you have to write down the values of the peak and RMS values of the fundamental component and the first 7 harmonics. Of course, the first 7 harmonics, since there are only odd components present in the Fourier series, so the first harmonic correspond to when n is equal to 3, and then 5, 7, and so on and so forth. And then derive the expression for the RMS voltage. Here again, if you would be doing it in the class, then you would have to show it here. Now this will be part of your lab report. Okay, next, Fourier series of the load current. Actually, that's circuit number 2. So this finishes up circuit number 1 basically. In circuit number 2, basically you're changing the load L1 and R1. R1 is 10 ohm instead of 100 ohm, and L is 31.5 millihenry. So now when you run the circuit, you expect, what do you expect? When these switches will be on, current is going to flow through Vs, M1, R, L, M4, go back to Vs. When these switches turn off, what's going to happen? Current is still not 0, and inductor resists the change of current. So what's going to happen? Current is not going to instantaneously change to the negative value. First, the current goes down to 0, and then it is going to go in the opposite direction. So for this circuit, the diodes play an important role. When these switches will turn off, M1 and M4, diode D3 and D2 are going to become forward bias, and the current is going to flow in the same direction as it was flowing through diode D3, Vs, D2, RL, until it will go down to 0. And then these two switches will start conducting the current. So the current is going to flow through Vs, switch number M3, L1, R1, M2, and back to Vs in the opposite direction. And when M3 and M2 will turn off, M1 and M4 will turn on, again current is flowing in this direction, It cannot instantaneously go in the opposite direction. Diode D2, diode D1 and D4 are going to turn on, and the current is going to flow through these two diodes until it's going to go down to 0, and then M1 and M4 will come into play and current will start flowing in the opposite direction. So let me show you the simulation of that. This is not the circuit. I think I closed the circuit. Let me see. Right here. So this is 10 ohm and 30.5 ohms, and I ran the circuit earlier, so this is the simulation of the current right here. So M1 and M4 on, D3 and what was that? D3 and D2 on until it will hit 0, and then the other two transistors will turn on and the current will flow in the opposite direction, and then the other two diodes will turn on. Current is gonna go again in the same direction, but it's gonna start decreasing and go back to 0, and then M1 and M4 will turn on again. So this will be the curve that you will see. Okay, now again we discussed how to calculate the Fourier series of the current. Make sure check out the lectures, and then write down the Fourier series, calculate the fundamental and peak value RMS as we did for the last part. Now then you have to calculate the total harmonic distortion. Peak current is square minus I1 peak is square. This is the formula. I1 is the fundamental component, I is the total current, and the total current peak value from the components that you derived over here, or that you calculated over here. The value of the peak current can easily be found out using this formula. The square root of I1 square plus I3 square plus I5 square, and so on and so forth, where I1 is the fundamental component, I3 is the harmonic 1, I2 is the harmonic 2, and so on and so forth, and all those values are the peak value of these components. So calculate the peak value of the output using this formula, and then calculate the output power, RMS square times R, and also the power corresponding to the fundamental component, which is I1. So in PSpice, how do you observe the Fourier transform? Here is the Fourier transform button right here. When you press this, you will see that it's going to show you the component on the frequency scale. The x-axis becomes frequency, and right now you cannot see anything because all the components are basically stacked over here. So let's go ahead and zoom that area in the corner right here. Okay, so as you can see, this is the fundamental component, peak value, n is equal to 3, n is equal to 5, n is equal to 7, n is equal to 9, and then it becomes smaller and smaller. You may have to actually zoom the area again. Let's see, something like this, and then you will be able to see all these components for the higher harmonics. Okay, so this is the lab. Make sure you have a good report, a thorough discussion of your circuit that shows your understanding of the project. Let me show you a report from spring 2018. Excellent report. First circuit, he did everything, created the table, output waveform, Fourier series from PSpice. Second circuit, measuring current that I showed you, Fourier series from PSpice, or Fourier component from PSpice, and all the RMS and harmonic values, calculation of everything that is required, and a solid discussion. So that's a really good report. Try to make good reports so you can get really high points. Next, we will discuss lab number 4 in the next video.